Ladies and gentlemen, welcome to the Ryan Ride Mechanic channel. How the heck are you doing today? Alright, today's show, what if I told you that this ride and this ride both use the same equipment? Well, they do. So they use a drive to move them around, and a lot of people don't understand drives, but they move almost everything in a ride these days. So I want to talk about what drives do inside rides these days. Let's get right into it.
Now get ready. Here we go.
First of all, welcome back. Thank you for joining me for another video. If this is your first time here, please take a look around, check out my other videos, see what's out there. I've got a lot of them, but I have a feeling you're going to be hitting the like and subscribe button pretty quick, so save the trouble and just do it now. Alright, so today's topic. These days, almost every ride out there uses a drive of some sort, whether it launches, whether it spins, whether it swings, whether it dives, dips, whatever.
If you can dodge a wrench, you can dodge a ball.
It pretty much uses a drive. So what is a drive? Why do we use a drive? And how does a drive work? First, let's talk about what is a drive. A drive is an electromechanical, pretty much an electrical component that sits inside of a motor control cabinet typically, and it is used on the ride to power motors. Now, motor being the key term, there's lots of different motors out there. You can use hydraulic motors that power a winch, let's say on like a Skyrush type ride where it's powering a cable winch up and over. You can use a DC motor, something like on a top spin. You can use an AC frequency drive motor, which is like on a lift hill to an RMC or something along those lines. Or you could use it into a typical AC motor that powers pumps and lots of other things. Lots of times booster wheels on rides are small AC motors. And then you could put them into bigger array motors, and we're going to say that this is where things like LIM and LSM technology come into play. And you could use them to power those as well. So all that stuff is powered by a drive. The drive in the back sits between the incoming power source and the motor, whatever you've decided to use. And the drive is there basically to get the commands from the ride and tell the motor what to do. The majority of parks out there use three-phase AC power, alternating current, because remember you have alternating current and direct current, AC and DC. So they use three-phase industrial power. Most parks in the US here use 480 power that comes in. That's the most efficient power to use three-phase drives at. You could use them on lower voltages, absolutely. You could even use small, really tiny drives and actually just plug them into a wall socket at home to run a really small motor. They sell those out there too. The drives are broken up into two categories. Now they both work very, very similar to each other. The specifics on how each one is different is uber nerdy, and it's stuff that I really don't even understand myself. I can tell you the basic principles, which is what I'll do, but I'm not going to get into the super nerdy stuff because I feel like most people just get lost on that, even the people watching this channel. Now, I know there's a lot of engineers right now that are pulling their hair out over that comment because they're like, why wouldn't you get into the really nerdy stuff? And it's like resistance, ohms, all that other stuff that is in the fundamental, like on the firing board of how it works. It's like, it's too far, it's too deep. I'm going to pull it back. Even for this channel, I'm going to pull it back, and I'm just going to stay at a higher level when I describe a lot of this stuff. All right, so two types of drives. You have AC and DC, alternating current and direct current drives. That is the output of them. Most of them are fed AC current coming in. So you have AC power coming in, and either it puts AC power out to the motor or it puts DC power out to the motor, depending on what type of drive you're using. Can you run DC into a drive and DC out? Absolutely. You can do that too. There are drives to handle that. Rides that use small battery packs and stuff on them, spinning rides where they have a motor to turn the ride, they are stored in a battery, so that drive is fed DC power, which is great. So it just loses one step in there, and you could feed DC power directly into the drive and get DC back out the other side to control your motor. For most of this video, though, we're going to be talking about AC drives, or alternating current drives, AC frequency drives, freak drives, whatever you want to call them. Like, we're going to be talking about AC type drives because that's the majority of stuff used in the industry. Both have their pluses and minuses, right? So it's going to be AC drives are used for typically fast moving stuff. DC drives are used for slow moving, really high torque things. For instance, a lot of roller coaster lift hills use a DC motor, so they need a DC drive to run that DC motor. But those are really high torque applications. A lot of flat rides use DC motors because they need really high torque applications in those motors, so they use DC drives. But most of the stuff around the park is going to be an AC drive, so that's kind of what I'm going to focus the video on, but I'll dribble back and forth between the two topics for sure. Okay, so where are these types of drive used? Let's look at something like an RMC lift hill. RMCs are great. They're typically lower cost, so what they do to keep the cost down is they use AC frequency drive motors at the bottom of them. Really big motors, but the cost of those are typically lower to both operate and maintain than the higher torque DC drives. So typically a like RMC lift hill would be an AC drive motor. If you look at the scenario of like a top spin, an old Huss top spin, those use 4 DC motors. So those will be a DC drive ride. LIM and LSM rides, you can throw them both into the same category. It's very interesting for people to think about it. Both of those are DC drives. And people say, well, no, it creates a wave that the ride runs on. It creates like an AC wave. It does, but it's using DC to do that. Everything is going positive and negative through those stators all at once when you break it down. So those drives are actually considered DC drives, but they mimic an AC drive form. And then things like flat rides, like a scrambler or something like that, they're going to use AC drives down at the bottom of them. Lots of AC drive motors because you can get them in high horsepower, but still a small frame where they're very cost efficient. So it's better for the ride to use AC on some of the smaller things. So almost everything in a ride uses a drive. Now, is it one drive per motor? That varies on the application. For instance, let's look at a B&M ride. Like a lot of times you have the station, let's say, where the train comes in and goes out. If you look into the station, a lot of times you'll have, let's say, about 8 booster wheels in there. All those booster wheels are run by an AC motor down at the bottom. They're typically something along the lines of a 1.5 to 3 horsepower motor down at the bottom of those things. They turn on and run all at the same time. So actually what you have on there is you have one drive running all 8 motors in that scenario. Now, all 8 motors are protected, so you break one, that protection will open for that one particular motor, and the drive can still run the rest of them just fine without that one. Again, DC drives are for more higher torque things. They're run both directions. I've seen DC drives used for like a swinging ride. I've also seen AC drives used for a swinging ride. It all just depends on the manufacturer and their specifications of what they're doing. If they're starting a big swinging ship side to side, they're probably going to want DC drives, like a Huss Frisbee. A Huss Frisbee has 2 very large DC drives on the bottom of them, so where they have to run a lot of current to get all that mass moving quickly, and then moving very high at the end of its swing. All right, so why is a drive needed? Drives are needed to start and stop a ride or a train. Like this could be used independent. So it's used for start and stop. Along with the start and stop, it's also used to accelerate and decelerate both of those areas as well. Just that little tiny bit of a ramp that gets into starting a train out, going out of a station, or bringing one back into a stop. The other thing it's used for is, it's the same type of thing, but instead of starting and stopping, we're going to accelerate and decelerate the entire load. So this would be something like a launch. This would be where like the Hulk uses a bunch of drive tires going up there. That's a very big drive moving all those tires together. If you look at more recent things, I know Intamin has built the straddle coasters out there where they used a tire launch. It's like the same thing. You have a drive or multiple drives in that case that are strung together to make all those tire array works. And then the last thing is the control of that speed. So when it's accelerating or decelerating, a lot of times you have to get it into a narrow little window where the ride has to operate. The window is very small. It's typically measured by RPM, stuff like that, but the ride's double and triple checking itself to make sure the ride is functioning in that window. So the drive is very necessary for speed control. It's one of the reasons, like when you get on a elevator, the elevator drive will lift the cab up at the same rate of speed whether it's full of people or empty, because the drive is exercising its speed control on the load. Alright, so let's talk about starting and stopping. Way back when they started putting electric motors on drives, you had two states, on and off, start and stop, basically. So what would happen is you would use a big motor and you would hit the start button, the motor would turn on at full speed. Well, as soon as it did that, it put 100% power to its windings, and then it tried to speed up the load from there. Now, you could do a lot of damage to the motor and the gearbox trying to pick up a static load that hasn't moved at all, and then suddenly just putting full RPM to it. So engineers used to have to do a lot of things to manage that starting and stopping. They did things like put fluid couplers and slip clutches in there so that when the motor suddenly turned on and fired, it would gradually pick up the rest of the load and continue to spin it. Fluid couplers are the biggest one that they would use for that. That allows the motor to start, stop, and then smoothly accelerate and smoothly decelerate down the other end, depending on how much fluid was in the coupler. The other problem with that is that when you raw start a motor like that and just say go, the power consumption is off the scale right when it starts. It jumps up and it goes to like 3 times its normal amperage that it should be running before the load picks up to speed, and then it comes back down to the amperage where it should be. So AC drives are put in and they can easily take that load and slowly spin it up and slowly move it back down and keep that RPM range right where it needs to be so it's nice, smooth, and consistent the entire way, and it keeps the current coming into the motor on the lower side too. So you have a power savings actually when you run an AC drive to a motor when you set the tuning correctly for it. The next one is positioning. So positioning is a really, really, really big one when it comes into amusement rides, because there is lots of positions that we always want a ride to be in. For instance, the first position that everyone enjoys is what's called the home position. When a train or something comes in, typically it has to slow down and stop in a specific spot. That is called its home position. Now, the home position is where people load and unload from the vehicle, but a lot of times it's a narrow little window because it has to line up with electric contacts, pneumatic rams and actuators to unlock restraints and things like that. So you actually have to line the train up in a little tiny little window. Well, on the older rides that didn't have drives moving trains in and out of the station, they would simply just let the train roll in and use pneumatic brakes to suddenly stop the thing. When they did that, the train would drift further forward or stop really quick, depending on whether or not there was load in the train, like a lot of people in there. So one of the things that you had to deal with was overshooting and undershooting that home position. So as the train would drift forward too far, it would overshoot the home position. A lot of times gates wouldn't open, you couldn't unlock the restraints and get people out. If it was bad enough, people might have been out past a platform where you couldn't even get the people off of that coach. Might have had to send them around again or something like that. Undershoots are the same way. If you can't stop in that little window, air gates won't open, restraints won't open. You have to manually open the brakes, let the train in a little bit more, close it back. So for positioning, we use AC drives now, or just drive motors in general, and we used a drive to bring it in at a high rate of speed, and then when it gets closer to that home position, we slow it down a little bit, let it come in a little bit, and then we slow it down even more, and then it gets right to its home position, and we go, kill it, right there, stop. And it's good. It lands in the same exact spot every time. Now, rides, they have a pretty big home position. Other things like swinging rides and things like that, they will not only home in one position, like for the swing, but they will home the rotation of the gondola until it's an exact spot where one seat might be facing its exact direction. So it's got multiple home positions that multiple drives have to move it into. You can go a little bit more complex and look at something like a flying coaster, like a B&M flying coaster. This is where you have to bring the train in, slow it down, stop it in an exact position, just like we were talking about earlier, but then you need a whole nother drive in order to lift the seat backs up just a hair. We're only talking millimeters, just a hair, enough to unlock the seats, and then lower them all back down to where the seats are in that load position and ready to go. And then we stop the drive right there and let everybody onto the ride. That is a very finite process, and you need a lot of control through that drive to do that. That sort of process wouldn't really be available with older technology. They would have to find some other way to do it, like a manual process to unlock and move the seats to where people had control over it, not so much on-off motors at that point. And then from there, you can move on to other drives used in rides, like, let's say, hasn't opened as the time of this recording, but the Fast and the Furious ride over at Universal Studios Hollywood, that rotates the coach around as it goes. It's the same exact thing with Cosmic Rewind. Same thing, it rotates the coach as it goes. Less rotation, but the same principle. Fly over at Phantasialand. It's like, does the same exact thing. It rotates the coach from the sitting to the flying position, 90-degree turn. So the next one is control of speed. Now, a lot of people don't really give drives enough credit for the control of speed on things, but engineers use this function way more than anybody else thinks they do. And once I start talking about it, it'd be like, oh yeah, that's it. Engineers these days typically opt to run motors at 75% of what they can do. Somewhere right around 75 to 85% of what the motor can do. Why is that? Well, that's a sweet spot right there where the motor is not full out 100%, which is maximum wear and tear on its motor. And once you drop below that threshold, it kind of also wear and tears the motor a little bit more on the bottom end, because some motors are not meant to spin that low down there on the bottom end. So it kind of wears them out, also the same as running at full RPM. But the speed control allows engineers to do things like put different modes onto the motors. It's like, okay, are we going up a lift hill? Yes. What are we at? We're at 75%, and that's what the ride runs over, and that's what we tune the ride to. Great. Is it cold today? Yes. Is it windy today? Yes. Ooh, we need more speed. What can we do? You know what? We're going to take that motor and run it all the way to 100%. It's like, great. That way we can get that train off faster.
That's what she said.
On the other side, and it can go through that course faster. Do we want it to go through that way all the time? No. So we're going to go in and select a special cold, warm up, it's windy mode, and get the train to fly off the end faster. Because that's what we want. Even with AC frequency drives, DCs as well, you can actually get the motor to go over its nameplate RPM. You can actually accelerate the motor to 110% of its nameplate RPM.
These go to 11.
Let's just say, make it easy, let's just say we have 1,000 RPM, and you say I want it to go, and you could crank the drive up and say I want it to go 1,100 RPM. It will make that drive, it will make that motor go 1,100 RPM. Is it tearing up the motor on the other side? Yes, it is. Can you burn it out quick that way? Absolutely you can. But can you do it? Yep, you can do it. Or I could slow it all the way back down to like 30%, 20%. Why would you want to slow it way down? Well, here's two instances. Number one is for the lift hills. It's like a lot of these things I could think of are for a lift hill for some of these bigger things. And all these can be DC, they could be AC. DC, I mean, it's easy to do the same exact thing. So on the B&M coasters, some of them you'll notice that as the ride is sitting there not being used, which means there's not a train on the lift hill, you could watch over and see the lift go into a slow speed. That's where the chain slows all the way back down, not to a stop, but it just slows down. So the reason why B&M lift hills do that is because they are using a chain oiler to oil the chain. Now at fast speeds, at full speed of that lift hill, the chain oiler can't efficiently oil the chain because it's moving too fast. So you have to slow it way down so that chain oiler can effectively, man, I can't talk this morning, drizzle oil onto that chain properly so it gets into the right spot. So they slowed it way down. Does every lift hill do that? No, they do not. Some lift hills actually do come to a full and complete stop. They stop completely. Now, they never used to do that because the amount of energy and wear and tear on the system it would take to start and stop one of those motors cold is absolutely ridiculous. It's crazy. Our old GCI, it had a on-off motor basically for the lift hill. So at the beginning of the day, you started the motor once and that thing ran all day long. Now, you had this big 150, 200 horsepower motor sitting down there, and when you hit the start button, it started all the chain, even with a train on top of it full of people. It just pulled all that stuff as fast as it could back into operation. It had a giant fluid coupler on there trying to take some of that torque out of it. But we broke the gearbox to that thing, I think 4 or 5 times in the time I was working there. It was a rough process to actually get that motor to start and stop and not just destroy everything in its way. So frequency drives are used to get in there and smooth that out. On the ride it replaced with the RMC, we actually put into a function on there and said, well, once it got up to lift park, if there was still a train in the brake reduction area down below, like operations for some reason didn't dispatch it in, which happens from time to time. So we said, if that train is still down there, we're going to stop it at lift park. And it was a colossal process to go out there, get people into the area to go up there to check on the train and restart it. That was the way our procedures were written. We had to go, manually check the train and make sure everyone was still seating on it before we could restart it. Pain in the butt. It was huge. So when we were programming it, let's said, hey, once the train gets to mid-lift, and the people that, guys, a lot of you know where I worked before. This is not a big deal, but once you get on that lift midway up, if you ever go up halfway up the lift and you feel that train slow down on the lift, and you kind of slow down for like 5-6 seconds and then you speed back up again, well, A, that's the drive doing that. But B, because we said, hey, if that train still hasn't cleared down below there and you're mid-lift, slow down. Because personally, I wanted to give the operators more time to get that train advanced into the station rather than just going the train on the lift at full speed up until the very top and then sticking it right there. It's like, I didn't want to do that. So I said, let's slow it down mid-lift, and then if it's not cleared, we'll stop it up on top. If it is cleared, we'll just send it right back up into full speed and up and over. And it works. It works a lot. Every time you slow down, it's like that came close to a block, which is where you would come up and just stop at the top of the lift hill. So it's like we managed not to stop the train up there because of that. Very happy. Okay, the next section is speed feedback. Now, speed feedback is done a couple different ways. Basically, speed feedback, we're talking about positive feedback from the ride. Now, what do I mean by positive feedback? I mean, when the drive sends its signal out to the motor, it uses a lot of technology to watch that signal go into the motor and then bring it back the other side, and it says, okay, I'm telling the motor to go at 1500 RPM, and the motor is in fact going at 1500 RPM. Therefore, the drive is stating that your motor is running at 1500 RPM. However, when you're talking about people, I mean, my old boss put it very plain and simple. When you're talking about making bottles at a Coke factory, at the end of the day, the guys walk through and they sweep up all the broken bottles on the floor. It's like, yep, that's what they do. Well, we have the same environment, but we're moving people. We're not moving bottles. At the end of the day, we can't go through and sweep up broken people off the floor. That's not going to work. Our accuracy has to be perfect. So we, in the amusement industry, we typically don't trust the drive by itself. We will use that information. We will say, okay, I'm doing 1500 RPM. It's like, whoop, great. We love it. Absolutely. Everything that you do, drive, keep up the good work. And then we use a positive feedback device and say, hey, what's this actually doing? So on the back of the motor, we will stick another device on the back of the motor. We either use, depending on the installation, it's either going to be an encoder or a tachometer. We're going to use one of those two. And then we're feeding that tachometer, typically, or an encoder, back to not only the drive, so the drive now has two sources of input for its speed, but we're feeding the other side of that typically into the ride's PLC, the ride control cabinet. We're putting that inside of there, and we're like, hey, all right, watch this speed. So now the drive is saying, hey, my motor is running at 1500 RPM, and the ride can actually look at that encoder or tachometer and say, yeah, it is running at 1500 RPM. I agree with that. The ride and the drive have to agree with each other. Anytime they don't agree, where the ride says you're going too fast and the drive says no, I'm not, or even too slow, fault, shut everything off. It shuts it off because now there's a problem with the feedback system, and we've lost our speed control at that point. We don't know how fast it's going, so we shut everything down, get everybody off because the conditions are now unsafe. So a tachometer is pretty easy. All it is a little spinning, looks like a drill motor on the back of the thing, and all it does is produce a little spike in voltage every time it passes around, and it's just a pulse, and the computer can count it, the drive can count it, and it's simply just a pulse as it goes around. It's not extremely accurate. It's meant to put out a frequency. Like as the motor's going, it puts out a frequency in hertz about how fast it's going for the drive to interpret the signal and make sure it's running its correct speed. Now, when we talk about homing things in the right spot, we use an encoder. So we use an encoder because we not only say that we want to use the same type of pulse, but we want an exact measurement. Every time that pulse happens, if I'm turning the gondola around on a spinning ride, every time that pulse happens, I need that pulse to happen every time I move the gondola 100 centimeters. As soon as I move 100 centimeters, it pulses. I'm like, okay. You think, well, that could be a lot, but you're talking about the motor through a gearbox, through a planetary drive, through a ring and pinion, like all these gears together. So all those things have to matter, especially when you're talking about timing things. So encoders are used typically when you need to stop in the exact position, when you have something that says, I have to be right here. The other thing about that, and this is kind of one of those areas I'm a little fuzzy in myself, but the other area is an absolute encoder. An absolute encoder does the same exact thing as an encoder does, but every time it makes that pulse, it creates in its processor, in the processor, it creates a word. Now, this is programming terminology, so I'm not going to get too far into it, but it creates a unique signature every time it sends that pulse out. Every single time it sends it out throughout its entire rotation, it creates a unique signature every single time. That allows the program to say, hey, when you're in this spot, it's okay to do this. When you're out of that spot, it's okay to do that. And then a lot of times stuff that's that critical, it also has proximity sensors double checking it as well. A good one for this would be a Huss topspin. Exact things. They use absolute encoders on there to ensure that everything locks up and spins the way it's supposed to. Why is it so critical? Well, let's look at things like over there in Phantasialand, Talokan, right? That was a really cool topspin. I got to go there and see that. That flipping topspin is awesome. But anyways, they use fire effects. Well, one of the things that you want to do is you want to lock out fire effects when that gondola is in a certain position. You don't want people too near, too far, something like that. So you want to lock those fire effects out. So from that absolute encoder on the side of it, you're going to say, hey, when you're in these areas, and you give it the signatures, and you say, when you're in this area right here, lock out the fire. We don't want that to happen. Also, when you're in these signature areas over here, the fountain can be at this height, it can be at that height. When you do this over here, it can be there. It's like, well, you can do that stuff with an encoder too, but you have to keep track of all the pulses. And the big problem there is that if you break a ring or pinion gear or something like that, those pulses go away. So one of the key differences there, I just now thought about this. One of the key differences there is that encoders are typically mounted on the motor itself, and the absolute encoders are mounted on, like on a Hus top spin, they're mounted on the side of the arm up in the structure. They're not on a motor, they're actually watching the arm angle itself as it goes up and rotates around. And then some DC motors, or I've typically seen these on DC motors, use what's called a resolver. This is actually like black magic mumbo jumbo. The resolver is a thing I know the absolute least about. Might as well be a foreign language to me because I really don't understand them. Basically what it is, it's a little generator on the back. So basically as the thing spins, it's generating some amount of current back to the drive to tell the drive that the motor is making the right speed. I'm really unfamiliar with using resolvers. I've only ever seen it used on one piece of equipment, and it was a pain in the butt when it went out, but we had to have SEW come out and replace the resolver on this thing because none of us knew how to deal with it. But it's basically a generator on the backside of the motor, but they're extremely rugged. For instance, that resolver that was on there, it was on the factory motor for 18 years, and then the resolver finally went out. I guess they could operate underwater and all sorts of stuff. So they're pretty rugged. People love them, but I just don't have a lot of experience with the resolver. Are you guys asleep yet? Did I lose everybody? I'm not sure. If you're still awake and you've made it this far, obviously like and subscribe to the video because that's awesome. Congratulations. This one might be boring for a lot of people, but roller coaster nerds out there for sure, this is all necessary to understand how your ride works in the end. So hang in there. Got a little bit more to go. All right, so how does an AC drive work? Let's talk about the drive operation itself. It's basically in three parts: rectification, storage, and generation. That's pretty much the way I say it. But it's actually, like when you talk about it, it's actually rectifier, bus, and inverter. The same process. So basically you bring AC power in and you rectify it. So what rectification does is you take AC power, which is positive and negative, it's going across a sine wave, up and down, and then you break it into DC, positive and negative, and you store it in capacitors on the backside of the drive. Now, depending on the type of system you're using, the type of drive, and like your power capacity with the motor determines the size of those capacitors in the background. But pretty much you take it and you put it into a bus in the back, which is DC power, and that allows that big wave to kind of disappear, and it kind of makes it solid. It still looks squiggly on the top and the bottom. It's like masking the center of the wave. It's like, oh look, I could see it, but you kind of can't see the center. It kind of looks like that. It kind of looks squiggly on both sides, but it's solid in the center. That's your power to work from. Then that's the bus. And then you go into the inverter side of it, basically, and you take that solid power, which was just your positive and negative, and you essentially put it back into an AC waveform. Although it's not a true AC wave, it's not going up and back down. That's what you get from the power plant as the rotor spins on the generator. So what you get out of a drive is more of a pulse. It's more of an off and an on, but they fire them in such a way to where the distance is spread apart and you get what looks like an AC wave coming out of it, but it's more of a square wave to it. It's like instead of being a nice curve up and down, it's more of a up, straight down, and you get that positive and negative in there, so it's feeding both sides just like an AC wave would. So the motor doesn't really know the difference between it. It's just like, okay, but you're able to modulate that waveform. You can make it taller, you can make it narrower, you can make the waves really long and far out and make them closer together. The peak of each wave is what you're typically watching. That's the hertz. So at a motor that's supposed to run 1,000 RPM, it will run off of, let's say, 480 power at 60 hertz. That means that wave, positive to negative, happens 60 times per second. That's the hertz. So if I want to slow that motor down, I just take that wave and fire it slower. That's where the drive comes in. So if I want that motor to run at 500 RPM, I'm going to run that motor at 30 hertz. If I want to run at 250 RPM, I'm going to run it at 15 hertz. Now the nice part about drives, like I said earlier, you can go faster. So I can take that motor and I say I could put not only 60 hertz to it, but I could put 90 hertz to it and make it go even faster, and that motor will go 1500 RPM for a short amount of time, but it'll do it, right? So it's like, it'll go faster if you put more hertz through the thing. Now, if you step back and say, hey, what's crazy? Let's look at crazy. Linear induction rides. That's so far been the craziest I've seen. The hertz output on those is crazy. When you look at how fast the thing is firing, supposed to be 60 hertz coming in. You got 60 hertz coming into the ride, because we're here in the US, it's 50 overseas. So you got 60 hertz coming into the ride. And then the output on full swing on that thing was like 125 hertz. That's like way out there, and the thing is moving like crazy, making all sorts of noise. Now, the act of creating a hertz on the other side through the drive motor kind of produces this little audible chirp sound as it goes through there. So that's one of the reasons why when drives move, you kind of hear this little high-pitch whining, humming sound. That's the AC form basically being made and sent back through that motor. Now, how it does that, it uses these things inside the drive. They're easily explained as a capacitor. It looks like a capacitor, it smells like a capacitor, but they're called IGBTs. The IGBT looks like a capacitor, but it stands for insulated gate bipolar transistor. Yeah, I forgot what it meant. I had to look it up myself. It's like, yeah, that's a lot of words put together. Looks like a capacitor, smells like a capacitor, but the difference is instead of having the power always on, you can actually put smaller voltage to it, kind of like a relay, and get the thing to fire and like only let that power out for a little bit. So it's kind of part of the control of the drive. Now, that's different from DC drives. The way DC drives work is the first process is the same. It goes in, takes the power, drops it off from AC into DC. Now it stores it on the DC bus in the background. Now the DC bus on a DC drive is extremely robust because that's its thing. It's in DC power. Now, it does not use a waveform to put it back together into the positive and negative. It uses SCRs to fire now between the bus and the positive and negative going out there to try to connect your phases, let's say 1 and 3 and then 2 and 1. You're trying to connect the phases at a time for a certain bit, and you're using that current from the phase connected at the same time to go into the DC motor. Now, I don't have engineering experience with drives, right? I'm a mechanic by trade. So my experience with drives is getting into them and say, why doesn't this work? You know, you will go into a drive and you say, oh, look, what'd this drive do? Oh, it released the factory smoke on the inside. The factory smoke sucks when it comes out. It really does. But a lot of times on DC drives, we had tons of them. You would go in there and it was the SCRs. The SCRs would break and they would essentially melt in the back of the thing. So it was a drive pit stop in there. You go take all the busing apart. You go pull out RS and T and positive and negative, and you take the back plane apart. You pull off the, let's see, it's 2, 4, 6. You pull off the 6 SCRs. You put 6 new ones on with some heat sink compound on the back of it. Tighten everything back down. Put the firing board back together. Good. AC drives, never really had that experience with them because they were very robust. They didn't break that much, and typically when they did, it was something stupid on the inside, like it lost its internal 24 volts, where it was just like, I don't know, something else went bad on the inside. Let's just get that off of there. Now, DC drives work differently because an AC motor, you simply put the 3-phase power back to it, back on L1, 2, and 3, RST, UV, and W, whatever you want to call it, and the motor just happily takes off on its own way. It creates its own fields up against the stator, turns the stator, no big deal, it's off and running. DC drives, however, you don't do that. You put the big power to the armature in the center with brushes, and you say, this is my positive, this is my negative, I want the power to run through the armature and make this magnetic field on the inside. Well, the DC motors that I'm used to working with don't use magnets on the inside. Like a lot of DC motors, they'll use a magnet in there for the other side of the field. So it's like, okay, you just put positive and negative, it creates that positive polarity on the inside and goes towards the negative on the magnet. Well, DC motors that we're used to dealing with in the amusement industry have a winding on the inside that is the field. So DC motors are actually controlled via the field. You take that current going through field windings and you can make it bigger, you can make it smaller, and the DC motor will do whatever it's going to do on the other side of that thing. Again, that's more into engineering stuff. Not on the engineering side. I'm on to the, oh, it broke, we need to fix it side of things. But I know one of the things when you have a motor that stops working, several times we went back to the drive and the field rectifier was burnt out and the motor just had no field to go with. Okay, so the last thing we're going to talk about kind of is control, and this is actually the thing, like I feel like I needed to go through a lot of this stuff to give you the basics of this. I'm sure everyone's clicked off the video or fallen asleep by now. I apologize. I hope you're having good dreams if you're watching it still. But the control of the drive is the number one question I get. How does this process work? What does this look like? Do you just hit the start button and it goes? Well, older drives, kind of yes. So, but they have wiring input at the bottom of the drive board. So when you're wiring up a drive, it's looking for all sorts of signals. Like, it doesn't know what direction it's going until you land a wire on there that says, hey, my 24 volts typically, you're going to go on to the forward direction, or counterclockwise or clockwise, whatever it might be. You're going to go there. And then I'm going to say, what speed are we going to go? Well, there's speed inputs down at the bottom of the board, so I'm going to put you on speed number 3. And then what do I want to do? I actually want it to speed up, so I'm going to run that wire through a relay, and then midway through the cycle, I'm actually going to energize this wire, and it's going to go to speed number 4. And then in the drive, I have to go in and program what speed number 3 is, what speed number 4 is. I have to give it ramps and curves in order to know that when it says to go from 0 to speed 3, it doesn't just go through the roof and just blow itself apart. I want it to gradually speed up. I want high torque. I want lower RPM. I've got to put all that stuff in there. The drive manufacturers made all sorts of little ramps and curves to go into programming and select each one and say, oh, this is what I want to do. When I say manufacturer, I mean manufacturer of the drive, not manufacturer of the ride. The drive is independent of the ride. So realistically, what happens is the ride tells the drive what to do. The ride tells it to enable, go forward, speed 1. And then after a while, you can go into decelerate, or you could simply just take speed 1 away and tell the drive to slow back down to its 0 speed, and it will do it. And when the drive says, hey, I'm at 0 speed, it tells the ride, I'm done, and then the ride shuts back off. The ride is done. Now, newer drives, that was a lot of wiring. There was some relays and things like that in there to run all that stuff. Newer drives now skip that whole input part down at the bottom, and the inputs are now basically safeties. Like, is everything okay? Yes, I'm going to run my okay wire to the bottom to say everything's okay. It's like, is my drive okay? I'm running that wire out of the bottom over here, and I'm going to give it a watchdog, and I'm going to run this to my e-stop circuit. If the drive says it's not okay, I'm going to drop the whole ride out that way. But a lot of that stuff is no longer done through wiring. It's now done through communication ports. So now the drive talks to the PLC directly and vice versa. Now, this happens on a lot of smaller rides and on all the big rides as well. But what's really critical is when you get into things like linear induction, linear synchronous style rides where they have launches where the drive is the block system to the ride. The drive is now getting all the parameters from the PLC directly. And then, so the PLC says, okay, what are we going to do when we go down there to launch, right? What are we going to do? Well, let's say the PLC says we're going to go forward. We're going to go in profile 1, and profile 1 has already been pre-programmed. But then the PLC might give it speed inputs. It says, well, you're going to go to this speed. and then you're going to use this torque value, and this speed. Now the ride is actually like making the acceleration curve as it's going. Where the drive just used to have that information in it. Now the ride is giving the information to the drive. So you're going to do this now, and it just gives it the recipe on how to get to that speed, and the drive is just there to do it. Here's the recipe, do it, and the drive does it. And then once the drive goes out, it relies on feedback from the ride. So once the drive is done doing what it needs to do, let's look at a ride like Top Thrill 2, right? It goes out there, it gets ready, the track goes back over, it locks into place. When the PLC says go, it says enable, and then it says speed 1, which is like in induction, like synchronous style rides, you call them, they're typically called profiles. So it's like profile 1. That means it's got this much torque, this much amperage, this much speed, all this other stuff, and the drive just gets that recipe and it starts to cook. It's like, let that drive cook, and it starts pushing that train down there. And then the ride is watching its sensors light up in sequence, and at the same time the ride is watching the feedback from the drive saying this is how fast the train is going. The ride has its own sensors along the track that is also running its own logic in those sensors saying that the ride is in fact going the speed that the drive is telling it to. So we're safe. And then once it goes out the front, the drive is like, I don't know what to do, but once it goes out the front, the logic in the PLC says, okay, drive, profile 2. Okay, profile 2. Now profile 2 has speed 2, and it's got this torque curve to it, and it's got a higher max speed, and it knows to switch into reverse now. And here comes a train off the tower, and as soon as it starts into the drive, as soon as the magnets get over those stators, the stators produce the feedback because the stators are the tachometer, they are the encoder. They are the analog, the absolute encoder too. So that produces the feedback, the positive feedback into the drive saying, whoops, I've got the train now. As soon as the train gets onto that thing, it says, I've got the train. And the drive picks up and says, okay, here I go. I'm going in reverse now. I'm going for profile 2. I'm going for this speed. I'm going for this torque. And that train just accelerates over the back end again. And the PLC the whole time is watching the sensors. It's watching the inputs, the outputs, everything. And it says, okay, yep, it's going for the right speed. And then once it goes out there, as soon as it gets up the back tower, the drive's like, I'm confused. What's going on? And the PLC says, no problem. Profile 3. Okay, profile 3, here we go. This speed, we're going forward this time. Now it's going to go for this speed, speed number 4, this torque curve, which is actually low torque, but it's high speed. And we got all these other parameters, and the PLC says, okay, the train should be here in 3, 2, 1. Sensors go high. Yep, there's the train, and then the drive suddenly goes, there's the magnets, and it starts firing again. It says, okay, DC, it sends that thing off down there, creates its wave. The train goes all the way up and over the top. And once it crowns over the top, the drive is just waiting there. What's drive do when it's in waiting? It puts itself into neutral, or it puts itself into a stop mode. That way, if the train were to come backwards at that point, it's stopped. It's just sitting there, waiting there. All the power that is generated from that motor can go through what's called braking resistors. Braking resistors are used all over all sorts of different types of rides. Sometimes they're on the drive itself. Sometimes they're big and external. But a braking resistor is just a giant resistor. It's a big coil that eats electricity, essentially. And then what you do is, as that motor is spinning down, if there's an e-stop condition or something else and you need that thing to stop, you take the power away from the drive. And as soon as you take the power away from the drive, a lot of motors will create electricity because you have that big armature, that big thing out there that's still spinning, running, rotating, flying, whatever it might be. And now you're making electricity, and that drive is free spinning. Now that can be really dangerous because it can blow out circuits and all sorts of stuff. So they take the electricity and they go, what do I do with this? And it goes, hook it to the braking resistor. And it goes click over to the braking resistor, and the braking resistor just eats all that electricity. Well, since it turns the ride into a generator at that point in time, the ride is now trying to power the braking resistor, which is essentially shorting itself together. It's like taking positive and negative and just go like that, shorten the two together. And because of that, the ride's like, I can't keep doing this. I'm losing my energy while it's turning around, whether it's spinning, swinging, whatever it is. It's losing its energy because all of its energy through that reverse motor, basically, the reversed process is going into that braking resistor and it slows it back down to a stop. That's what braking resistors are used for. Different size braking resistors used for different things. When you go up onto a LSM ride, and they hit the e-stop and you drift back in there and the thing comes to a really fast stop. A lot of us have seen this before on all sorts of rides. What they've done is they've disconnected those stators from the drive, and they've connected those stators to a giant set of braking resistors into the back area. And every time one of those magnets crosses the coil, where the drive was producing a field in the coil, now the magnet is producing a field back into the coil, and it's going to the braking resistor. But, like I said, it makes the whole thing run in reverse, so now the whole thing slows back down to a dead stop. Kind of went too far into that, sorry. I have a video on how LSM rides work if you want to watch that specifically. Check that video out, LIM and LSM rides. I got both of those videos on there. Anyways, I've probably lost most everybody on this. Let's see, did I forget anything? Oh, yeah, I did forget. Forgot to talk about a function that Allen Bradley uses in a lot of their drives called safe torque off. All right, safe torque off is a function as the drives get smarter, we trust them more and more because the safety rating on the drive has actually come up. The drive's safety rating is now almost as high as the roller coaster safety rating itself. So that means engineering engineers can trust the drive more. It's got enough safety and feedback in it to where they trust it more and more and more to do what it's supposed to be doing. For instance, a lot of times when you bring a ride home, when you home that train in the home position, we used to say, turn the drive off, and the drive would shut off, and then we would take contactors, which go in between the drive and the motor. We would take contactors and open those up. So even if the drive decided to turn on and go, it couldn't, because the contactors were open. So we physically disconnected the drive from the motor as a safety feature. Well, as the safety rating of drives get up higher and higher, we now trust the drive to make that decision for us. So what it is in Allen Bradley ones anyway, it's called safe torque off. I'm going to read this here because I took the time to write it down. Again, this is more in the programming and engineering side of things. So it's the stuff I never really had to deal with. This is like, here's the safe torque off wires. I just knew that this is where the wires had to land on these terminals, and it was critical for function of the drive. That's kind of what I knew at the time just working on them. This is more in the programming side, so there's a lot of information here. I just want to read this real quick. On the Allen Bradley drives, the safe torque off function will prevent the drive from moving unintentionally. So now when the drive comes in and stops, the ride is in a position, the controller will feed voltage either physically or through I/O cards and tell the drive to go into a safe torque off mode so the drive cannot move anywhere. Once both safety channels have deactivated, this is internally in the drive will be in safe torque off mode and can no longer function until the signal is on, both wires are restored. Okay, so you had the two wires coming in for safe torque off. Basically what you have to do is you have to energize those wires to give it the command that it is safe to move. And then once you say it's not safe to move anymore, you take the two wires away and it says, okay, it's not safe to move anymore. The reason for that, power outage. You blow a fuse or something else like that. If I blow a fuse on the electricity on those wires, I want to make sure that taking the power away from those two signals, the safe torque off signals, I want to make sure that those don't tell the drive, yeah, go ahead and move, it's fine. I want to make sure when you take those wires away, the drive says, nope, it's not safe to move, we are stopping. So these are typically done in conjunction with the stop commands as well. So we tell the drive to stop, and then we remove the safe torque, or we give it the safe torque off signal, and the drive also feeds back to the PLC and says, yep, I'm in safe torque off. It's safe to load and unload. Places where we use this all the time, loading and unloading things that spin. Right? The drive is not necessarily disconnected from the ride completely physically. It's still connected, but we've essentially immobilized it internally because of the drive safety rating. We've given it that safe torque off function, and it says, okay, I can't go anywhere now, and the safety ratings have proven that it can't go anywhere, and it doesn't, which is what makes the ride safe to load and unload. Dog walked in for the end of the video. She's a good doggy, though. Anyways, that's it for this video. Long one this week. I know a lot of times it's like half an hour. It's so short, but this one's going to be a long one. I hope everyone's still awake. If you haven't already, subscribe to the channel. I really appreciate that sort of stuff. Like it, share. You can even use the, what's that new function YouTube put in there? Is it boost? No, it's not boost. It's a hype. You could use the hype mode on things like that. When you see a video comes out that you really like, it's like, hype it up. Go ahead. If you want to email me, you can always email me at ryantheridemechanic@yahoo.com. You can always leave a comment down below there too. I try to answer comments as often as I can. Sometimes they're very cryptic and I'm not sure what the comment was intended for, and I can't answer those really. All right, that's it. Stay off the air gates. Bye.